thumbs up also, just to see how that looks, because I'm a little new to the Teams browser environment. I mostly do on Zoom and other things. Can we see how the reaction looks? Give me a thumbs up. There's a react button, I believe. Yes or no? Okay, I don't see how that looks actually. Okay, that's fine. We'll keep the chat. We'll interact on the chat itself. All right. Okay, so let me start the session, since all of you can see my screen. GenAI in media and entertainment. Okay, so let me just introduce myself quickly. I know all of you have already heard this. My BTech was from NIT Surathkal and PhD from IIC Bangalore. And I always loved to teach. And fresh out of my BTech, this was, I graduated back in 2010. Fresh out of my BTech, the most logical thing for a person who wants to teach was to do PhD. And there, during my PhD, I got the good fortune of taking a lot of rigorous mathematical foundational courses, which even today help me in my journey in machine learning, GenAI, and so on. Right? So probability, linear algebra optimization, and so on. By the way, this is my LinkedIn profile QR. In case you guys want to connect with me, feel free to do that. You can just scan this, or I can even share the link if you're interested. Okay. Oh, I now see the thumbs up coming up. Okay, I see only Asha and Ashwini being active. All right, that's okay. We have more than 80 people, but I hope all of you will soon start getting interactive. Okay, so fresh after my PhD, I got in touch with the co-founder of a company called AlphaISys, which was developing a deep learning inference chip, and I had the good fortune of working closely with the founding team there. And optimizing deep learning inference chip was what I did there. I also moved to Target, where I used machine learning in supply chain. At Harman, it was a computer vision project where we were doing driver monitoring system. And I'm currently even taking a consultant role at a company called Unicode, which is also a startup, and again getting to work closely with the founding team. I've also been an instructor at Scalar. I still teach there occasionally. And I've taught more than 2,000 students, where we built a solid data science and machine learning curriculum. All right. So feel free to hit me up on LinkedIn. We can also get on a quick call in case you want to keep the discussions more engaging up beyond this call, right? It's not that we are only meeting each other once. Okay. All right. So that's about me. Regarding the session, first thing I'll ask is this is for GenAI, right? So Gen stands for generative. Okay. So if I want to ask, apart from GenAI, right? If I say GenAI versus something else AI, what would you say is that something else, right? If you're given a qualification or an adjective like generative, what is the other types of AI that you know? Please type in chat whatever you think is the other part of AI, because I called it generative AI, right? So think of it like this: if I say he's a tall boy, then there is scope for someone who's a short boy, right? Similarly, if I say generative AI, what is the other part of it? Can someone quickly guess? It's okay. There's no right, there's no right or wrong answer. Just can we just have a quick interaction in the chat that guesses what is the other type of AI? Anyone can, if you want, you can unmute and talk also. No one? Any? Okay. How do I motivate in? Okay, all of your faculty members, right? How do you motivate interaction with your audience? I'd like to learn. Or is there
Yes, sir.
By means of some games.
Sorry, Asha, please go ahead.
Sir, some sort of games.
Games
to make them interact, like to make the audience interactive. We can.
Okay, some sort of games. Okay. Okay, I'm currently not. I don't have any games right now. But yeah, anyway, can someone guess what other type of AI we are talking about? If you talk, say, generative AI on one side, what other type of AI are we talking about?
Actually, sir, we are creating an artificial intelligence in any machine so that it will work accordingly. Generative AI is something different. It means we just say, and there is no any command or just it will work accordingly and it will do its task.
So what's the opposite of it? What's the if it's not generative, what's the typical word that you can use for the other type of AI maybe?
Means,
Okay, I'll
for
provide,
example,
yeah.
We say robotics are just as robotics. Suppose we are creating artificial intelligence, it will work automatically.
Okay. Okay, fine. That's one aspect of Gen AI, but I'm stuck. Okay, so the typical word people use is discriminative AI, right? So generative and discriminative. Of course, you may also use words like predictive or something like that, but typical language in machine learning is talking about discriminative AI. Now, how do these two types of AI that we mentioned here, how are they related, right? So I'll show a nice example. The reason I'm going into this depth is because I want all of us to understand the nitty-gritties behind Gen AI. How is data represented there? Right? What are the key tools that will make a Gen AI happen? And then we can, when we talk about how it is done in media, like for example, diffusion models and so on, it makes a lot of sense once you know the internals of it, right? So that's why I'm stressing a little more on this aspect, right? So now this is a cat, right? All of us here can look at this and say this is a cat, okay? Now just that mapping, giving an image and calling it a cat, this was part of what I call discriminative AI, right? Where you have given the computer an image and asked it to say what it is, right? In fact, this was not a very trivial problem. About 10 or 12 years ago, neural networks were not very adept at least for larger images and so on, right? Sometime in 2012, a landmark paper came called AlexNet, which worked on the ImageNet, huge data set on ImageNet, and that helped computers to quickly look at this image and say what this is a cat. Now, why is this a difficult problem? We'll get to it. We'll get to the internal representation of images presently. But until then, just hold on to the thought that this was not an easy problem about 10 to 12, more than 12 years ago. Right now, it's a very trivial problem. Okay. All right. Same thing. Any other image of cat you give, maybe a new image you give, this time it will call it a dog and so on. Right. So these are all. This is a very naive example I'm giving. Right. And this it will call an elephant. Right. So this was very easy. Even a 3 or 4 year old boy will start doing these things, right? But computer took a lot of time. Why is that? We'll soon see. Okay. Now, in the language of literature in AI or ML, we use symbols like X and Y. Okay. So X represents my data here, and Y would represent what I'm going to call labels, right? Labels mean it just it's telling you what category that object belongs to. In this case, it could be simple animal categories, right? So here X denotes data, Y denotes labels, and the mapping that you go from left to right. Notice this arrow that just came up, right? Mapping that goes from left to right is telling you that if you give this as an input, then I'll give this as an output, right? That part is discriminative AI. All right. So mapping from X to Y is discriminative AI. In this specific example, it's called image classification. So then what about generative AI? Generative AI is like saying, hey, give me an image of a cat, right? Give me an image of a cat, and then it is actually going to generate it, right? Brahmapal, right? As you mentioned, you don't have to do much work in generative AI. You just say, hey, give me an image of a cat. Most of you would have used ChatGPT or any of these existing chatbots or LLM-based chatbots out there, and the ones with the power to generate cat will immediately give you some image like this, not necessarily this image, right? It'll give you some image like this, all right? So that part, the inverse of this mapping, right? If I look at this purely as a mapping, then this ulta, right? This inverse going from Y to X, that's one way of looking at generative AI, all right? It's not a simple task, as I said. Why? Because it has to generate all the pixels, right? Some of you who may have an understanding of what images are, at the heart of it are what are called pixels. Pixels are nothing but matrices with values, right? And based on red, green, and blue, it has to generate so many values in such a specific manner for it to resemble a cat, right? So this inverse of it is called generative AI. And you can, many of you would have done something like this, generate an image of a dog or something like that, right? And it would have given you this, all right? So this is a high level understanding of generative. If you want to look at it as a system mapping, I would say give an image of a cat. In the discriminative AI, it'll give you cat, whereas in the generative AI, it'll give you a dog. If you say give me a picture of a dog, it'll give you a dog. All right. Now the big question here, right? Why is this challenging? Okay. So you must think, hey, I have millions of images today, right? If you can use tools to scrape websites, whichever are freely available, you can have millions of images of cats, dogs, computers, tables, water bottles, anything, right? So what's the challenge there, right? We have labeled data. Why can't we just return an image of a dog from this data, right? I just ponder here. Why can't I just return an image from an existing data? What's the problem here? Can someone guess? Brahmapal, since you're very since you initiated and since rest of the people are not very interactive, can you also please help me here? Can you help me understand why this is a challenge here? Anyone else, of course, not just Dr. Brahmapal there. Anyone willing to keep the interaction flowing?
Actually, sir, if we want to, instruct to our machine that give me an image, so if there will be a labeled data, so classification, identification, such kind of things will be difficult for a machine to understand, I think.
No, okay. If there is labeled data, it can give you images from the existing data set itself. But what if you give a crazy prompt? So what is a prompt? When you say something like, give me a picture of a dog, you are the language you use to give an instruction to the generative AI, let's say an LLM based AI system, that's called a prompt, right? So the complexity of the prompt, the kind of things you can write may not always exist in that large labeled data set of yours, right? Even though you may have millions or billions of images, you may ask in the prompt, you may ask, give me a picture, give me a cartoon picture of a green dog sitting on a beach where there are 3 people behind it, 2 people in front of it, one fellow has a hat, right? Now that specific detailed version of such a image might not even exist in your data set. Yet the AI algorithm has to know what is a animated image or a cartoon image. What is a green dog? What do you mean by 3 people behind, 3 people in the front, one of them having a hat? It has to choose which of these people should have a hat and then put hat only on that, right? So it has to understand the nitty-gritties of a language, which can get very, very complicated as you write more and more sentences. And hence the need to able to encode each of these information in a very sensible manner is what the generative AI algorithms are currently doing, right? They are trying to capture the nitty-gritties of so many aspects of the data set or of your prompt so that it can generate it. That image does not exist, right? So the challenge is that image does not exist. Okay, now let's look at a fun example. I'll try to motivate this fun example. Now, this is an image of a lion, right? Yes or no? Is it an image of a lion? Yes or no? I don't see chat rolling. Have people just
Are you asking that image is aligned, sir? Are you asking alignment of the image, sir?
Lion. I'm saying this is this an image of a lion?
Lion is not there, sir.
Okay.
Lion.
So this guy writes, give me a baby lion there. Okay.
Baby lion.
Yeah. So what happened? Where there is a dog, suddenly there is a lion. There's a lion cub. Okay. So now imagine the complexity of the task here, right? This is a model called Flux. Okay. Imagine the complexity of the task. You have an image which has a dog, and in the very let me run this again. This was the original image where this guy has a cute-looking dog, beagle or something, sitting on his lap, right? Then he tells the AI algorithm, sorry, he tells the AI algorithm, hey, just replace this dog in the exact location that the dog exists. Replace the dog with a baby lion. So it has to not only generate an image of a baby lion, it has to occupy approximately the same space in the image as that of a dog without without having inconsistency, right? Like that. Now this looks fairly genuine. The image of a lion looks fairly genuine because his hand is in the front, the lion is in the back, right? So imagine the complexity of the task where you can isolate a specific region in the image and then say replace this with something else, right? This is like fairly recent stuff, right? We are talking about something that was released I think July, August-ish, something like that, right? So this is fairly recent stuff, and the complexity of the task is what I want you to appreciate, right? Because it is giving you such a nuanced picture of what is going on, right? Like for example, you can say, hey, replace this coffee cup and maybe keep a large glass of lemonade there. So it has to remove the pixels corresponding to the coffee cup, and then it has to replace it by a large lemonade, where it has to hide the chairs that are behind this, right? If it's keeping a large glass of lemonade juice or whatever, right? It has to hide that and then fix it, right? So imagine the levels at which the AI algorithms are understanding the images. Now anymore, it's no more about just pixels per se. It's able to understand that all of these pixels here correspond to a dog. Now you may think, hey, when he did this coloring, his leg is also shaded, right? Like if I rerun this, his hand and all are look at his hand, right? He covers his hand, a little bit of his leg, all those things are covered in the white mask, right? So he's given a mask to the AI, yet somehow it makes sure that the hand is not missing. It makes sure that the pixels around the leg are not touched, even though when he shaded it, a little bit of the leg pixels were covered, right? So it understands your statement saying that, change the dog but not the man, right? Keep the rest of these pixels intact, maybe regenerate some aspects of it, like the position of the hand may change a little, that's fine, but the exact place where the dog is, replace it by let's say a lion or something, wherever you're given a prompt. So there is a image masking thing, there's a text saying baby lion, replace it there, right? So this is the kind of advances that's happening, where people are using GenAI in media entertainment and all, right? All right. So now that we are sufficiently motivated about the use cases of AI, let's again take a step back and go into the internal representations of how these images and even text, right? While this example is on image, even in text, it can happen, right? You can give a very complicated thing to ChatGPT or something, and you can see it generate fairly decent stuff, right? Now, if I say I like pizza, right? The discriminative part of AI here is simply saying good or bad, right? Is this sentiment good? If you see this in a Zomato review or a Google Maps Pizza Hut review, this is a good sentiment, right? That's sentiment analysis. But then you may say, hey, generate an good review for pizza, right? So this is where generative AI comes in, where it has to now come up with new words that describes this, right? So it can say delicious pizza with a great variety of toppings, crust, blah blah blah, right? So this is an example of a text using GenAI in the text domain, right? This is very common. If you ask ChatGPT to write a good review about Pizza Hut, it will just do all that and give you a fairly convincing string of text, right? That almost makes you believe a human wrote it, right? Most of GenAI is like trying to mimic a human, but maybe even better, right? Humans couldn't easily replace a dog with a baby lion when we draw. Most of us, I don't think, can do that, but GenAI is managing to that. Whereas these simple tasks like reviews and stuff, obviously we can write stuff, and GenAI is doing a decent mimicking of that behavior, right? Now let's look at the challenge here, right? I alluded to an example in the past which said, green dog with 3 people in the back, 2 people in the front, something like that, right? So you may think, okay, generation, right? So what if I randomly generate? We all know how to generate random numbers, right? You can toss a coin, you can or use basic Python NumPy random numbers to generate, right? So why is generation a problem? We can generate pixels, right? It's easy to generate pixels. If you look at image space, let's take one of the most common data sets out there, right? This is the MNIST data set. People use this a lot in machine learning training and all that, right? So, and the dimensions for this are 28 by 28, right? So it's fairly small, right? It's very small image. The cameras, the phones that we have are talking about megapixels of camera. This is just some 700 odd pixels, right? It's a very small image. Yet, if I randomly generate, randomly generate black and white pixels, imagine how it will look. It look like pure noise, right? Now, if I keep on generating and generating and generating until it looks like, let's say, a 6, okay, just to generate this specific picture, just to generate this, you will need something like 1 by 2 power 784 basic probability, right, to generate exact picture like this, right? 2 power 784 might have 200 digits in the more than 200 digits in the representation, right? So even if you have the best supercomputers out there, if you keep on generating randomly, you may never be able to see a sensible image coming at all, right? And this is just for these images. Now imagine your own phone. Your phone might have 10 megapixel, 20 megapixel, something like that, right? And then there is RGB behind it. Okay, so then uh, lifetime of the universe, if you generate randomly, you might not even find a sensible looking image, right? Most of that image will look something like this. If it's a binary 0, 1 images, it look like this, right? Most of the images that you generate, you'll never be able to find a sensible pattern. The chances are it's not even 1 in million, 1 in trillion, it's 1 in 10 power 100, 10 power 200, something like that, right? Even more than that for you to find a sensible image, right? So this means that generation per se is a fairly tough task. All right. So when we go to color images and still lower, it becomes fairly tough. Okay. I'll give one more example before going into the data set representation. All right. So this is about a dice. Okay. Again, to talk about generative versus discriminative, right? If I have a fair dice, I'll see a sequence like this, 4, 3, 5, 4, 1, something like that, right? Most of the numbers will almost equally repeat. Okay, but if I have an unfair dice, which is based on its dynamics, lands on 6 about 90% of the times, then what happens? Well, most of the numbers will look like 6, right? If you look at this data, most of it looks like 6. All right. So this is about whether I have a fair dice or not. Now again, I can ask two types of questions here. One question could be, given the sequence, you have to say whether it came from dice 1 or dice 2. Okay. This is one example. The other example could be, given a dice, you want to generate a sequence typical of that dice. Meaning, if I tell you dice 2, you should continue the sequence as if it's coming from dice 2, right? That's a harder task. The first part is the discriminative part, where you have to say whether it's dice 1 or dice 2. The second part is the harder part, where it has to look at patterns of data and start mimicking that data. Okay, so this is where GenAI, the algorithms behind GenAI, starting from GANs, variational autoencoders, all the way up to the diffusion models and transformers today, right? What are they doing? They are able to look at patterns of data and then create more such data points as if it resembles this, right? So if I manage to understand the dynamics here, this is fairly simple because I've given the rule. 6 appears 90% of the times, other 5 are, let's say, equally likely. If I tell you that rule, it's very easy. It's 4 lines of Python code, right? If I tell you the pattern, however, when you're giving large scale images, right? When you're giving it millions of images and so on, you don't have uh, any rules that says pixel values here should be gray, pixel value here should be blue, nothing like that. There are no rules, right? You have to just look at the data. That's what these algorithms have to do. They have to look at the data, try to capture the essence of the data, and be able to mimic more and more such data. Okay, and the next level is putting control in it, right? That guy put a control when he said, in this area give me a lion. That's next level stuff. Whereas at the very heart of it, even looking at existing data and generating more such that it resembles it, you should not directly give it that data. You may have thousands of dog images. You can't just pick a dog image and show that. You have to generate a completely new image that will look like the dog image to the human eye, right? You just have to, at the heart of it, you have to deceive the human eye to generate more media content. All right. Okay. So with that, with these setups, right, with these examples of image generation and this data set, the reason I give this is because it's a very simple example. We can keep this at the heart of our mind, at the back of our mind, right? Whereas image generation is what the ultimate theme of the data should be. Now, my point is that no matter what your data set, right, no matter what your data set, it could be text, it could be speech, it could be music, it could be images, right? At the heart of it are what are called vectors. Okay, and these vectors are what drive the image generation. Okay, in fact, since since we have talked about text a little, right? Suppose you take up your let's say you take your WhatsApp, you take WhatsApp and start typing stuff. Say, just type how and are. What will happen? What will WhatsApp recommend if you type in WhatsApp, if you type how and then are? What do you think will happen? What will you see as a recommendation? Let's see how many of you are active. Chat, please. You take WhatsApp. I'm sure all of you have used WhatsApp. You type how, you type are. you type 2 words. What in chat? Tell me, what are the possible words that you think WhatsApp will recommend for you? No one has used WhatsApp? Okay, thank you, Sharath, for being active. Mohan, sure, you can unmute if you want. Okay. Is that all, Sharath? Is that all they'll recommend? How are you? Maybe how are things? Right? Something like that. Okay. Just take WhatsApp if it, or any, not just WhatsApp, any predictive text, right? If you take that and type, it'll suggest the next word for you, right? Am I even audible to some of you? Because it's the least level of interactivity I was expecting.
Sir, it's audible.
Yeah.
Huh?
It's audible, sir.
I just don't know why WhatsApp is, I mean, sorry, the chat is, yeah. Okay, fine. So it'll give you these recommendations, right? So what is it doing at the heart of it? It is saying, let's say you have x1, you have x2, right? X1 and x2 are the words. Okay, then it has to give you a candidate for x3, right? So then it's trying to compute probability that x3 is equal to, let's say, u, given that x1 is equal to how, and x2 is equal to r, and so on, right? Something like that, right? So it's looking at the past data or context and then predicting the probability for a candidate third word, that is x3, third word, right? And if this is high, it will recommend it. If it's a completely if it's a word that never comes in the context of how and are, then that word will have a very low probability, right? So the heart of it is computation of probability, right? So we will see how, whether it's image generation or text generation or anything, we will see how the internals of it work. All right. Okay, so this is about understanding probability and vectors, and we'll take an IPL example. Okay, so suppose we switch on the TV and we find that our team has scored 90 runs in 6 overs. Okay, with no loss of wicket. How do you feel? How do you feel about you switch on the TV a few minutes late, but you find that 6 overs are done. Your team has scored 90 runs and not lost a wicket. How do you feel? Anyone? How do you feel about that situation? Okay. Shaktivel, thank you. Thank you for still being around in the call. Looks like most of you have logged off, right? Is it like this? Is this session like a mandatory thing where you have to just log in, keep the computer on, and go home? Yeah. All right. No one else. Okay. There's just one person. Expect more meaning. Okay. So let's look at how data is represented, right? So I have overs and score in my X and Y axis, and I feel happy, right? So six overs, 90 runs is a good score. All right. 6 overs, 20 runs is a bad score for me. Okay. So I have associated the situation of a cricket match into a scatter plot where I have 6,20 being bad, 6,90 being good, and so on. So anywhere on this plot, we have a certain emotion. Maybe 6,60 is neutral emotion, right? But if we just put it into binary, we are happy and sad, let's say. Okay, so good or bad, something like that, right? So we are looking at a mapping again, where the elements of the set of my set X are now overs and score. Earlier, it was images in the very first example, text in the second example. In this example, the X data is overs and score, and Y data is good and bad, stuff like that, right? So I can look at all my X data to be of the form X1 comma X2, where X1 is overs and X2 is score, and Y data could be simply good and bad. I have just let's say I have just 2 classes here, all right? So the way to capture this, saying that, you know, if my team has scored 240 in 20 overs, right, that data point is somewhere here at the top, right? In 20 overs I've scored something like 240 somewhere here, right? So then I feel good. Now suppose when I say I feel good, I have to quantify it, right? It is observed that 95% of the times the team wins, having scored something in the range of 240. Okay, let's say 95% of the time the team wins. So in this context, very similar to the conditional probability that I have written here, conditioned on the past words, what is the future word going to be, right? Similarly here, I can have a conditional probability. I can represent this with a conditional probability that says probability that Y is good, given that you are in this specific state in the match, is 0.95. Okay, so this is how the again, this is still in the discriminative setup. This is how you are mapping a point to 20, 40 with a value good by looking at the conditional probability, right? P of Y given X, conditional probability is what is what you are captured, right? So now why is this important? Why is this data, this specific example important? This example tells me that apart from the images and text and so on, right, even understanding the dynamics of a cricket match, right? Like when Shaktivel says he feels happy about this, how do I convince a computer to feel happy, right, when it looks at this data, right? Meaning, can I give it the last 10 or 12 years of IPL data, ask it to analyze it in a specific way, and tell me whether I should feel happy with this score or not, right? Most of machine learning is trying to teach machines to mimic human behavior, so that sentiment of happy and sad or good and bad got captured in my labels, and that mapping of between left hand side and right hand side here is happening via conditional probability, and it's saying that I'm 95% sure that I'm in a good place. I'm almost willing to bet. If you score 240, you're probably ready to bet in that match, right? If it scored 270, you're probably bet even more. 300, I don't think has ever happened, but you'll bet even, you'll be more confident about betting, and that confidence is captured in some sense in this. It's called a posterior in the language of statistical machine learning. All right. So now if you go back to the dice example, right? Here in the discriminative setup, you are doing P of Y equal to dice 2 given the whole sequence. Meaning you give me the sequence, I'll tell you whether the probability, what is the probability that the dice, so here Y is whether it's dice 1 or dice 2, right? Y is the label and X is the data. Same as our original image example, all right? So whereas in the generative example, you give me the dice 2 and I have to give you data like this, right? So you give me a prompt saying generate dog, and I have to give you pixel values of a dog that looks like a dog, right? Give me dice 2, I generate data. So I want all of us to be comfortable in understanding that at the heart of all of this is simple probability. All right. Now, if I go back to the previous example, why this example? This example specifically because I can look at this data point as a vector, right? This vector is nothing but in the x-axis I have 6, and in the y-axis I have 90, right? Most of us write vector as a column matrix here, column vector here, or you can also write 6 comma 90. That's also fine, as long as you know stick to one convention, right? Most of us write it like this, right? So now understanding vectors, understanding a scatter plot, and understanding the ability to associate each value in the scatter plot to a emotion of good or bad is something that should come very natural to us now, right? So while we're talking about IPL example, all we did was consider a scatter plot, and for those of you who are already familiar with machine learning, you know how this will look like, right? You know that you know that we are talking about data set where the yellow points will be at the top, the blue points will be at the bottom, and what is a typical classifier supposed to do? Let's say you run a logistic regression or an SVM or something. What's it supposed to do? It's supposed to draw a line and say anything below the line is one class, anything above the line is another class, and so on, right? So we are in the setup of binary classification, right? Logistic regression, SVM, even tree-based methods, you can draw all that, although it won't draw a line like this, it will cut it parallel to x-axis, x and y-axis multiple times and so on, right? So there are many ways of doing this classical problem of binary classification, right? However, our purpose is not to go there today. Our purpose is to understand how the data is represented in a GenAI setup to understand vectors, probability, and that can take us into that leap of understanding diffusion and image generation going forward. All right. Okay. So vectors and probability. So these are two of the most important skill sets to understand the more advanced techniques out there. All right. Of course, in probability, you would want to know things like KL divergence and maximum likelihood and all that to understand the math behind diffusion models. Right. Diffusion models today are at the heart of generating images. All right. Okay. So now that we have that picture, right? The next important thing is understanding how probability also comes in image classification, right? We saw probability in IPL example. That was a simple example, right? We all know that if you score 240 runs, you are most likely going to win the match. All right. So now let's say you show this image to a image classifier, right? It will not, if you take one step before the final answer of cat, you will actually see, if you're in the ImageNet setup, you'll see 1,000 values post a softmax operation. You'll see 1,000 values that will actually talk of probabilities, right? Now, most likely it's a cat, but the computer might also see some similarity with the cheetah, maybe, right? So it might even have a small non-zero value for cheetah. It might this may look like a flower, maybe a flower vase or something, right? So that's possible. The shape of this may, if you squint a little, you may think it's some sort of a flower, right? Or maybe a lamp. Okay. So if you squint even further, it may look like a lamp, right? So these values typically add up to 1 in a probability setup of an image classifier, right? So, and these are conditional probability. Given this image, what is the probability that it's a cat, right? Conditional probability is at the heart of most of these algorithms. Just like in the text example, we saw conditional probability. Sorry. Just give me a second. In the text example, we saw conditional probability, right? Similarly, in the image setup also, we want to see conditional probability in a very similar manner. Is 1 second. I just closed the app by mistake. Okay. All right. Now, generally when I teach, people are more interactive. So I ask, is this a cat or a dog? So can someone guess? Is this a cat or a dog? Okay. So the reason I ask this is because this is what a computer sees. Okay. I've dumbed down the image a little by making it look smaller, but it's actually a bigger image. So if I ask a computer whether this is a cat or a dog, one image looks like this. It looks like 3 matrices of RGB, one behind the other, combining together to give me a color image, right? If the values are high, it'll be white. If the values are low, it'll be black. Okay. And it can be either from a 0 to 1 or a 0 to 255 typically scale. All right. So images are nothing but matrices, which again are nothing but vectors, right? Larger vectors with a specific shape and form, tensors or whatever, right? Vectors, matrices, tensors, you can think of them as high dimensional vectors as far as I'm concerned. All right. Because the addition properties, all those things still hold good, right? This happened to be a cat. It's a one I myself held in my hand and took a photo of. And these 3 combine together to give you an image of a cat. Okay? So the nitty-gritties behind understanding image generation requires you to understand the pixel space. That is what I just showed. The values of those pixels. So those 3 values on the R, G, and B scale, they're talking about pixels. And the ability to use this image. I remember function mapping, very first slide, that's what we started with, right? Take a function, the input is the image, or rather than the image, it's actually the bunch of vectors or matrices that we just saw. That comes in as an image to the function, and then it has to output whether it's a cat or a dog or whatever, right? Or in the language of the posterior probability, it's looking at p of y equal to cat given x. Given the image, what is the probability that what you have is a image of a cat? Okay, and if that is high, you say it's cat. If that is low, or wherever it is high, that is the label you give it. All right. Okay, so this is us staying in the pixel space, taking a simple example, and whatever I've covered so far wouldn't have been a very challenging thing, right? Because it's something we're all familiar with, because most of us may be in the field. Whoever's been in the ML field, most of this is familiar, right? Now, but why did I spend this time? Because I wanted the idea of a vector very thoroughly sitting in our minds. Okay, so if you look at and in today's class, I won't look at how text is converted to vectors. That's called embeddings, and that's a slightly longer we'll need a much longer session if you want to look at how text is converted to vectors. But at least from images point of view, right? Images point of view, right? Images as vectors. I hope this is fairly simple, right? Images as vectors is fairly simple, because ultimately we have a we have these red pixels. There is R, G, and B, right? So the values in this is these places will be filled with actual numbers from 0 to 2, right? You can look at that as a large high dimensional vector. Okay, your megapixel camera you could think of as a million length vector, and into 3 if you have RGB there, right? So images as vectors are fairly straightforward for us. Okay. Then we also looked at an IPL example where we decided to use x-axis as overs, right? X1, then X2 as runs. Now you can think of more and more features, right? X3 as let's say wickets, right? X4 could be who the opponent is, right? X5 could be which ground you are playing on, and so on, right? But at the end of it, you're still talking of numbers here. Just like in the image examples, we have numbers directly coming to us from the camera sensors itself, and when you store it as a JPEG or a PNG, you have the numbers directly here. Whereas here you are forced to a physical phenomenon, like a cricket match, and you have chosen these as features, right? For images, typically, luckily for us, existing pixels itself you can use into a convolutional network and extract features in a more automated way via neural networks. Whereas for a specific example like IPL, you may want to handcraft these features, right? And it's up to you to decide which features you want and so on. So most machine learning algorithms, you may either handcraft and do some feature engineering. If it's images, it might come readily available to you, right? Now text, well, text is a little tricky in the sense that you need algorithms. I won't go into the details of this, but you need algorithms like word to vec. In fact, even more bag of words. These are classical stuff, right? Bag of words and TF-IDF and so on. Okay, these are just words I'll write in case you want. And if you want to pursue this in more depth, you can go and search about it. Bird, sentence, bird, and so on, right? In fact, BERT happens to be a very I think 5 or 6 years back when BERT was released, it became very popular in terms of encoding, and it will ultimately convert text into vectors, right? So images as vectors are understood. IPL kind of example as vectors are understood. Text to vectors, again, as I said, while we won't go into the nitty-gritties of the algorithms, just take my word that they're also vectors, right? Now, what are one things we like about vectors? We can always draw a scatter plot. Okay, can always draw scatter plot vectors. Now, generally we can only see 2 or 3 dimensional scatter plots. To visualize high dimensional scatter plots, there are techniques like PCA, T-SNE, and so on, right? So typically we have high dimensional scatter plot, but just for the sake of visualization into a 2 or 3 dimension, right? We cannot visualize 3 dimensions. Also we can visualize, but beyond that we can't. So visualization 2 or 3 dimensions. Typically, we'll use something like T-SNE or PCA, UMAP. There are a lot of techniques out there, right? So your high dimensional vectors, your million scale images, you can still compress it, in some sense, compress it down to 2 or 3 dimensions and still visualize them on a scatter plot. Okay. So when you visualize vectors on a scatter plot, it might so happen that the cat images could be here, the dog images could be here, right? Your computers, images of all computers could be here, right? Images of all, let's say t-shirts could be here, maybe different color, right? Something like that, right? So this is what you want in a very good representation of images as vectors. Similarly, as for words as vectors also, right? You want a representation, a vectorial representation of whichever modality of data you're using. You would want it such that they are, you know, uh, 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 images of a specific category you want nearby, images across category you want far away, right? This will give you a very nice representation. And now the generation aspect comes, where if you say generate an image of a cat, the idea is to sample from a probability distribution of the cat data set distribution, right? So we imagine a hypothetical cat data set distribution, and then maybe not give any of these existing points, but somewhere in the vicinity here, there could be an image of a cat, right? And use that to generate. All right. So the idea behind generating images, in at least in what is going on now, like last few years, is what is called a latent representation. A latent representation forces images to be vectors of a smaller dimension. Instead of your million scale pixels, it might be thousands of values, right? That might be enough to capture the nitty-gritties of images, right? Images are heavily redundant. This was something known to people in signal processing long back, right? Wavelets and so on, right? So those modality, those algorithms manage to compress images very much. How is that? Because if you look at take your own selfie and look at it, notice that around your face, almost all the pixels are very similar value, right? Only when you move from the face to the background will the pixel value suddenly change, but then background might again have similar values, right? So there's a lot of redundant information in the image as is, right? Now deep learning and GenAI techniques have managed to compress your millions of values of pixels. Instead of using those many numbers, hundreds or thousands may be enough, right? And that happens via latent representation, where we use what is called an encoder, right? You take your image and you encode it in a specific way. All right. Okay, so let's look at, and then we can talk about generation. All right. Okay. So in the latent space, we have, let's say I have an image. Okay. So what is it that I want of that image? The original image will be in high dimensions, right? Millions of values of pixels. Okay. The typical way in which the algorithm should do is they will take this high dimensional. So when I say high dimensional vector, you should imagine like a million numbers here, right? In a specific shape and form. Imagine the RGB matrices all flattened out to be a long vector for now, right? So this is a high dimensional vector that I'm talking about. And any vector that I get, I can reshape it into those dimensions and call a IM show or something on matplotlib to see it as an image, right? So a bunch of numbers for a computer, image for humans, right? The medium that to interact with it could be a simple matplotlib call, all right? Or save it to a JPEG and open it in any of your favorite image editor, all right? Okay. So now this comes into through an encoder, which is typically a neural network, okay? And what comes out of the encoder, remember, this is just the encoder part, right? What comes out of the encoder is a low dimensional representation, okay? And this will be a this is called a latent space or a low dimensional representation, okay? So here, instead of millions, we may only be dealing with thousands, okay? So what is the advantage in here? The advantage is that very often people have found that there is a nice arithmetic that exists in the latent space. Okay, which means if I take a photo of myself, and if I take a photo of an old person, right? That gap, the typical person, let's say photos of people typically in their 30s versus photo of people, let's say, in their 80s, right? There is some changes that happen, right? Your skin might wrinkle a little, your hair may gray a little, right? And so on. So there might be those nitty-gritty changes that happen in the images of young people versus old people, right? And what this latent space can capture, and it has been shown to capture, is that there is a arithmetic that happens where if you add, so if I again go back to my scatter plot kind of a thing, it might so happen that there is some dimension for the old people, such that, and young people images, right? There may be some vectorial way of taking an old person's image, adding something in the latent space, something belonging to young people, and then generating an image that will now look like the original person, except that you'll have made him or her look younger, right? Many of you may have used GAN based apps like Face App long back, right? So this all this was done several years now. GANs came out in 2014, and by 2016, 2017 itself, people had amazing apps that were able to do this, right? So the ability to reduce that. So this could be along one dimension, right? Or one or two dimension or more. Now there could be other things, like I could take my own image, right? So I could look at images of people with glasses. Like suppose I want to see, can I take this photo of mine from a nice background? I've taken a nice vacation background, but my specs was not very appealing in that photo. So can I do some sort of Photoshop and remove the glasses, right? So then there are people without glasses. So there is this is without glasses. Okay, so there is some in this latent space, in the arithmetic of behind latent space, there could be some dimension there which kind of captures whether the person has a glass or not. And if you move sufficiently away from it, it might end up generating your own face but without the glass, right? So all this showed the power of latent space, right? And even today, um, uh, the diffusion algorithms, there's this brilliant paper by Stable Diffusion, which somehow looks at latent space and runs its diffusion algorithms there. Okay. Let me just pause here and wait for some questions. I don't know if I'm going too fast or too slow for you. Okay. So I'll just pause, and I'll hope some of you ask me some questions so far before I jump into the demonstration of diffusion. Anyone? Any questions? Anything? No? Yeah, Sharat, I'll continue, but I'm just waiting for some questions. It'll be a monologue otherwise, right? I generally don't like monologues. I was hoping a little more interactivity. Okay, fine. So, so what happens with the encoder? Once you encode it, what happens? And how is this related to generation? Let's see that. Okay. So in the latent space, my images of cats and dogs could be like this. Okay. I'm just again giving a very simplified version. These spaces will be in thousands of dimensions. This could be my cat sitting here. There could be my dog sitting here, right? And I could think of absolute pure noise, right? The one that we generated in the very beginning. The noise could be somewhere here, right? I'm just throwing some rough sketches here. Okay. So the idea behind diffusion, which is today powering a lot of how GenAI happens in media, right? how are we generating, like what I showed earlier, right? Where a dog was replaced by lion and stuff like that, right? So a lot of these apps, Midjourney, Runway, and all, Dali, and all that, they understand latent space, and they understand how to navigate in the latent space, right? Even GANs, where in some sense, if even though people have moved more to diffusion now than GANs, uh, uh, despite that, even GANs were handling the latent space quite well, right? It was shown these arithmetics were fairly captured uh, by GANs. In fact, you can, if this is space representation of cat, and you move a little towards dog, you might start getting images that have some features of cats and some features of dogs, right? Like the ear might look like a dog, but the nose might look like a cat, and so on. So you'll get this hybrid kind of images. In fact, I still remember there was someone who gave a prompt of what was that, avocado, I think avocado like chair or something like that. Okay. And then Dali or something, it gave you an image of a couch. Yeah. A couch that looks like an avocado, something like that. Right. So then it gave you an image of a couch, which let me see if I can go online and actually get that. Okay. It was Dali avocado chair. See that. Okay. So this is fairly surprising quite a few years ago now. So this looks like a couch or a chair, right? Looks like a chair, but it also looks like an avocado, right? So that was that was quite fun. Then there is this whole this person does not exist.com. Okay. Um, this is GANs. Okay. As far as I remember, this came up a few years ago when GANs were very popular. Right? So every time you refresh, it will generate a person which will look fairly. I mean, look at how accurate it is, right? You have light. You can almost feel that the light is coming from this direction. Therefore, this part of the nose is lit up. This part of the forehead is lit up. This part is dark. Notice how close to accurate it is, right? So every time you refresh, it will generate or it will give you a generated image or something which looks fairly accurate, right? It's hard to believe that it's fake. All right, we know this is fake, but this is what I was saying, right? You have this feature space in which you can move around, and then you can do funny things, right? So the original example that I mentioned at the beginning, where I said, give me a green dog with three people and behind, two people in the front, all those things end up being very trivial if you can do something even crazier, where you're taking two objects and trying to, in some sense, in the latent space, interpolate between these two objects and then generate an image which surprisingly looks like both a chair and avocado at the same time, right? So this was a fun example where the math that we might see, or the scatter plot that I was trying to motivate, actually results when you go back into the higher dimension. So there will be a decoder here which will go back into the higher dimension and generate your million scale vector, which you will reshape and plot or show, and that will now look like an avocado chair or whatever that means, right? So you can mix and match. You can make yourself older or younger. You can remove your specs. You can and then there is this more advanced stuff where you can specify a specific location, and in that location you can ask it to edit. This is what we saw in the beginning, right? Okay. So we will look at one such modality, or rather one such algorithm that will generate this for us, right? So we look at the geometry behind it. Now the algebra behind it requires us to know things like maximum likelihood and KL divergence, and it's a longer derivation, right? While I would love to teach math, math being my forte, where I love teaching, but because of the time constraint and stuff, I would rather not go too deep into the math. I'll try to motivate it visually only. All right. So let's so this is one example I often show in when I teach diffusion, because this kind of is easy to relate to. Okay, so suppose you want to be a bodybuilder. Okay, now how do I mean, how I clearly don't look anything like a bodybuilder, right? Because none of the features that you attribute with a bodybuilder do I have. Okay, neither the bicep size, waist size, body fat percentage, overall bulk, overall weight, overall strength. I don't have anything remotely close to what a bodybuilder is. Okay, now because we are understanding images, because we are understanding latent space, and because we are understanding scatter plot, we will motivate the idea behind diffusion using a scatter plot, which in your mind you should quickly relate to the images also, right? So suppose I do one example here. Okay, so suppose I have bicep in inches and body fat in percentage. Okay, now I'll break this into 4 pieces: A, B, C, D. Okay, look at it carefully and tell me, where do you think bodybuilders will lie? X-axis is bicep, y-axis is body fat. Okay, think carefully. If I roughly split it into A, B, C, D, okay, where do you think bodybuilders will lie? Will they lie here? By the average bicep size is, I think, in the range of 12 or 14 or something. Okay, if you have a tape later, go ahead and message. Okay, again, it might change across gender, but somewhere here is the average body. Okay, and body fat might be in the 15-20 region or something, or maybe more based on how much we eat. Okay, so where do you think your bodybuilders will lie? Will they lie in A area roughly? Will they lie in B area? Will they lie in C area? Will they lie in D area? So I have about 156 people in this call and only one person answering. Is it so tough or is it too easy? D. So Archana, I'm saying that average people have biceps of 12. When if you're saying B, so will the body fat of a bodybuilder be high or low? You're a bodybuilder, body fat, remember, not weight. Just tell me, will the body fat be high or low? Body fat is expected to be low for a bodybuilder, right? Okay. Bicep is expected to be high for a bodybuilder, right? So bodybuilders will end up lying in this area. Okay. The actual numbers we may not know right now. That's okay. But you expect them to lie in this area. You expect them to have a higher bicep and lower body fat. Whereas we might end up in this area. Okay. Meaning our biceps will be more or less average, most of us, right? Body fat depending on how our eating habits and our genetics have guided us, it will be here, right? Some of you may be in here where bicep is also very high, but body fat is also high. Okay, dad bods, that's what they're called, right? Okay. Archana, yes, high bicep, low fat. Okay. So if we look at right? So if I just generate some example of this, I would expect most of us sitting here today, all the 150, I don't know, maybe there are some bodybuilders here, I don't know, but I'm guessing at least 150 of us will be in this area, right? And bodybuilders will probably be in a very small location here, right? 18, 19, 20 and all. I don't know if 20 has been hit, but maybe it has, yeah, right? And very low body fat, right? Maybe 3, 5, 10, like something in that range. Okay, so you'd expect bodybuilders to be here, you'd expect us to be here. Now, the same example of cat and dogs, avocados and chairs, IPL examples, they're all vectors, therefore they all have a scatter plot, but we are only representing it in a 2 dimensions. Why? Because we cannot represent of course, I could be a little innovative and draw a 3rd dimension, make the ball bigger if it's nearby and smaller if it's far away. Those things I can do, no doubt. But for the sake of intuition, we are only using 2 dimensions. Remember that, right? And remember, in the case of images, we might be actually talking about 1,000 dimensions. Okay, so keep that at the back of your head, because when we speak of this generation, we're actually doing in that space, right? That latent space is where we are doing the movement. This bicep example is just a simpler thing for us to grasp. Why? Because suppose I want to be a bodybuilder, right? Suppose I'm here somewhere and I want to be a bodybuilder. What will I do? I'll go to the gym. Okay. And when I go to the gym, I might, over a couple of weeks, I might increase my bicep length. Okay. and reduce my bicep body fat a little, right? So I've gone a little to the right, a little to the bottom. Okay. I might next week I might think, hey, I'll cut down on all the fatty foods and go down a lot on my body fat, right? And so on. So I am in some sense moving closer and closer until a point where I can fool the people into believing that I'm a bodybuilder. Once I'm here, I can walk into a contest, right? And at least people will be fooled. They'll think that I'm a bodybuilder. I may not be able to register or something. There may be other parameters out there, but at least people will feel, fine, this guy belongs on the stage rather than the audience, right? Most of us may belong in the audience. Okay. So moving in a way where you can fool people into believing that you belong to this category, right? Starting from a original data distribution and adding the right, using the right amount of algebra to move in this latent space as if it's a sample from a different distribution, right? We are almost talking of a bimodal distribution here. You can, if you're familiar with Gaussian mixture models and all, you can think of that, right? You're almost thinking of that. You have data from one mixture and another mixture, but can you do some arithmetic where you can add and subtract and so on? So here I'm adding bicep, subtracting body fat, right? That's what I'm doing. Okay. So can I do that and reach the structure of a bodybuilder, right? So this logic, since the example is simple to understand, notice that we are only adding and subtracting, which you can still think of adding a positive number or adding a negative number. Okay, we can still keep that concept in mind, right? So now if I go into the latent space, if I go back to my latent space, okay, I'm thinking of, can I start with absolute noise? Okay, so what are these points here? Each point here is a latent representation such that the image, or rather the decoded image, looks like this, right? So here I am in the pixel space, meaning the actual image. Here I am in the latent space. Okay, so the latent space will be of lower dimensions. In this case, I'm only showing 2. This will be in the million dimension pixel, right? So this is pixel space. I can see it. This doesn't make sense to me because those 1,000 numbers will not make sense to us. Okay, we will not be able to make sense until we come up into the higher dimension via decoder, and only then we'll be able to see it. Okay, so that is the high dimensional picture that I have here. The low dimensional stuff is here. Latent space stuff is here. Now what should I do? Just like in the bodybuilder example, just like in that example, I was adding bicep, subtracting body fat. Similarly, in this latent space, now I don't have values for my x and y axis, right? In the bodybuilder, I had values for my, I knew what my x and y axis were, bicep and body fat. In IPL, I knew what my x and y axis were, runs, score, and overs, right? So I knew what those things were. Whereas here I don't, right? There's no logical thing for us right now because they are nothing but output of a neural network, which could be taking your million dimensions and making it smaller and smaller in almost an encoder. For those who are familiar with autoencoder, variation autoencoder, you can see those architectures that go from high dimension and keep going lower. But once it goes lower and you look at the final encoded value, there's no name for it. There's no name for the first variable. So this is a vector. These are 1,000 numbers, right? There's no specific name for it. However, its properties are observed when you do addition in this space and then you view it in the higher dimension through a decoder. Okay. So similarly here, in this space, I can do my additions and subtractions and look at it here. So now what happens if I run this algorithm? Okay. So let me just if I do this addition in a manner similar to my bicep increase and body fat reduction, I might go one step. Okay, notice this. I'm going one step. Okay, I'm going one step. I'm just redoing that animation, right? I'm going one step in the latent space. That one step in the latent space will typically be written as xn plus 1 is equal to xn plus some epsilon. Okay, in the literature pertaining to diffusion models, you'll often see this kind of an equation where epsilon is drawn from a Gaussian distribution with a mean and some variance and stuff. Okay, of course there will be some specific beta terms or something hanging around, but ultimately it is adding noise. Okay, it's adding a Gaussian noise to that. Now, the way you add and subtract is something you have to be very careful with. Okay, and technically, in a diffusion process, there is something called forward and reverse, where in the forward you start from the cat and go to the noise, whereas in the you start from the noise and go to the cat. So right now I'm showing you the reverse diffusion, but just to be technically and pedantically correct, right? You start from, in the forward, you start from cat and dog and add noise and go to a Gaussian. And the reverse diffusion or the generation or the inference is where you start here and then go here. So I'm showing you the reverse diffusion part. Okay. So as I do that, the image generated might look something like this, right? There's a lot of noise, but hidden somewhere inside it, and that's the beauty of diffusion. Hidden somewhere inside it, we can almost spot a cat, right? Not yet properly, but we can, because we already know that it's a cat, we can probably see the outlines of a cat, right? This is exactly what happens in an actual diffusion setup. If you run the code that are there out there, you can actually see these things happening. Okay, and then when you add more noise, when you go closer, when you denoise, so this step is called denoising, reverse diffusion. When you denoise, you go closer to your target. So now I'm in this example, let's say I'm tracking just one. So what is here is just one point here. Okay, one vector in the latent space is what I'm tracking in this space. I'm not showing all of them here. I've indicated maybe 10 or so points, right? But what I'm doing is I'm just sticking to one of them and showing it at different stages. Okay, just keep that in mind. Right? And as I go further, the latent vectors or the generated reverse diffusion or the denoise vectors end up going and sitting somewhere in the latent space representing of the cat. We are still in this dimension, and then via a decoder, they might end up coming to me in the higher dimensions, and now I'll see a full-fledged cat. Okay, the equations behind it are adding Gaussian and a very clever way of subtracting Gaussians. So it's not, I mean, you can't exactly say subtracting Gaussians, but a very clever way of undoing the noise. Adding noise is simple, undoing is difficult. A simple example is, as kids, we have all gone to the beach, we have created a sandcastle, right? It's very hard to create a sandcastle because you have to take wet mud, you can keep on tapping it and doing that, right? So that part is hard. But destruction is very simple. You just jump on it once and it boom, that becomes noise, right? So one part is very simple. Making it look like noise is very simple. So starting from a cat, right? Starting from a cat, adding noise is very trivial. All of us can do it. np.random, right? And adding more noise is again trivial. np.random again, right? Again trivial. np.random or torch.rand, whatever, wherever you are running, CPU, GPU, wherever, right? It's very simple. Okay. And there is sound theory that says that if you add it with a specific sequence of variances, it'll have the property that when you compare it with a Gaussian, pure Gaussian, the KL divergence between what you have generated and the pure Gaussian can be very small, right? So there is a sound theory that says if you take small steps in the adding noise framework with the specific sequence in which you add noise, the distribution of the noisy version of all these data points and the distribution, or rather the samples of the noisy versions here and the samples of a pure Gaussian, among them the KL divergence between those two can be made very small, meaning to the human eye, when you show it, it will not be able to realize whether it is pure Gaussian noise or whether it's generated this way, right? So it look like pure Gaussian noise, and that's what we have here, right? So take a cat, forward diffusion, make it fully noise, reverse, take noise, undo the denoising part. That's very tricky. That requires a lot of theoretical understanding of how that happens. All right. Okay, so I will I'll end my this is a good point to stop here, because if you start more details of control net and stuff, we won't be able to cover it right now. I think this is a good point to stop and give some time for Q&A, right? So please Please feel free to ask me questions, and whoever wants to follow up or connect with me, I think I've shared my LinkedIn ID with you. You can ping me there. Let me also, we'll be happy to have more conversations around this. Okay. I don't know if I've sent a chat message. You can click there, or if you're more tech savvy and want QR codes, you can have that. Okay. All right. I'll just leave the field open for 10 minutes of questions. Otherwise, we can wind up. Any questions? Feel free to unmute and ask questions.
Participants, if you have any questions, you can raise.
Was it a useful session? Did you feel like you learned something or not? I don't know. Sarath, online courses for what? What topic? Diffusion itself. You can, if you want a theoretical, if you want a practical course, you can go for Hugging Face diffusion course itself. Or for GenAI in general. Okay. Again, Hugging Face itself has a good amount of resources to learn from. So that's a nice place to start. huggingface.com/learn. Okay. That has a good amount of resources. Again, as I said, feel free to ping me one-on-one, and I'll be happy to jump on a LinkedIn call or a Zoom call or whatever, right? If you want a more structured roadmap based on where you are, what skills you have, and what skills you want to pick up, we'll be more than happy to jump on a call and help you there. Okay. All right. Anyone else? Any other questions? Let me share the link of the Hugging Face course if anyone's interested. I think this session is recorded, right? So I'm hoping most of you will see the recordings, because live interaction suggests it was a formality, right? Okay. I see no questions. I see no one raising hand or asking questions. So we can call it a day. Shakti, prerequisite to learn GenAI would be understanding, first of all, the math that we spoke, right? You already saw vectors, so understanding linear algebra and probability and optimization. These are the mathematical background that you need to have. You need to know, ideally, PyTorch. If you're still stuck with TensorFlow, that's also okay. And then it is, if you want to be hands-on, it's possible to jump into the Hugging Face courses. Whatever theory is required, you can pick up as and when needed. But those courses should help you, right? There's a course on NLP. There's a course on computer vision. There's a course on diffusion itself. There's a course on reinforcement learning. Okay, on that website. So, and then there is a community maintained cookbook that you can glance through, see what is interesting and so on, right? AI agents and RAG and so on. Yeah. Okay. Anything else?
Yes, sir. Can we wind up the session?
Yeah, we could. Yeah.
Okay. So, on behalf of our institute, I extend a heartfelt gratitude to Dr. Ajay Shenoy for delivering an exceptional session today. Your ability to break down complex concepts and explain them with clear and practical examples truly enhanced our understanding and engagement. Your depth of knowledge and the way you connected theory to real-world applications have left a lasting impression on all of us. We deeply appreciate the time and effort you dedicated to sharing your expertise with us, and we look forward to learning from you again in the future. Thank you so much, sir.
Yeah, thank you. All right, everyone. Thanks a lot and bye.
Thank you, sir. Okay, thank you, participant, and you can join back tomorrow.